Well, hello everybody. We're going to go over the second page of this paper. So let's zoom out. Part 1, I went over questions 1 through 11, I believe it was. So now we're over to here, number 12. So explain a conjugate acid and base pair. Well, whenever we have, a reaction where I think, okay, let's say we've got HCl plus water changing, or actually in equilibrium, and it's forming H3O, hydronium ions. Boy, make sure you got that. Hydronium ions plus, and let's see, chloride ions. Now this would be in an aqueous solution. That means there's water formed here, because whenever you mix an acid and a base, they're going to neutralize each other. They're going to form a salt and water, and these are kind of the salt part of it on here. So what the conjugate is, these are going to be the conjugate compounds that are formed. These are basically they're the products that are formed over here. Now, when we take a look at this H3O plus, it had to have had this hydrogen come from there. And since this is donating the proton, this is the acid. And since this is accepting the proton, this is acting like a base. Now, when we talk about the conjugates, these are going to be the conjugates over here, the things that are formed. Now, one way you can tell which is the acid, this has a plus charge. Acids, all when they ionize, are plus charges. Just like a hydrogen ion is an acid, it has a plus charge. And this has a negative charge, so this is going to be the base over here. So this will be the conjugate, the compound that's formed, base, and this is going to be the conjugate acid. Since HCl, well, we took away the proton there, so this was acting like an acid here. Over here, it's going to act like the opposite, because conjugates are kind of, they're the opposites. So that's how that is. So when we're asking for the acid-base pair, if we say the conjugate acid and base pair, well, here's the acid, here's the base. If we're asking you for the acid and conjugate base, this would be the conjugate base. So hopefully we don't trick you with wording on the test. So in this one right here, well, these are all on this side going to be the conjugates over there. And okay, well, since this is ammonium, that proton had to go this way. And so this, since this is accepting a proton acceptor, this is the base. And this is acting like an acid because it's donating a proton. So the conjugate, now the opposite of this over here is going to be this one. This is the conjugate, and since it was a base here, it's going to act like an acid, which should make sense because it's got a plus charge. And over here, this is very definitely, that's a base, but it's going to be the conjugate base on there. Okay, over here, let's see now. We've got this hydrogen has to come over here in order for this to be H3O plus. So it turns out this is going to be our conjugate acid, because this is what's formed. It's a conjugate, and since it's a plus charge, it's an acid. Since water over here was accepting a proton, it's acting again. It's a proton acceptor. It's acting like a base. So it's conjugate over here. These kind of look the same, just one more. So it's going to be the acid over here, and it has a plus charge. Over here, okay, hydrogen had to give one of its protons to water to get this formed. So this will be the conjugate acid over here. And this will be the conjugate base. It's got a negative charge. Over here, this was acting like an acid because it was donating a proton. But over here, it's going to be the conjugate base, and that makes sense because it's got a negative charge. Okay, number 14. Let's see, I got to zoom out for this one, sorry. Can't get it too close here. Now, first off, when we see kilocalories, just put heat, okay, just so I know. It's just telling you how much heat, but anytime you see kilocalories, that's just the same thing as saying heat. What reactants and products are in the following? Are you kidding me? That easy? Okay, this is a reactants over here. These are products. What is the reactants in the, okay, we got nitrogen gas as a reactant, we got hydrogen gas as a reactant. the right side of the equation, we call these the products. We've got NH3 or ammonia gas, plus we've got heat as a product over here. And since heat is being given off over here, this would be an exothermic reaction. If heat was required over here, then it would be called endothermic. Well, let's go to number 15. Why is this reaction endothermic or exothermic? Well, it's producing heat. Let's make that heat. So it'll feel hot to us. Feels hot, and that my memory clue is it's extremely hot. So this would be exothermic because it's producing heat. Now, if we had a reactant and we needed to add heat, and it formed a reaction and we got a product over here, since heat is over here, this would be endothermic because heat is going in. If we mix this together and got this reaction going, the flask that it's sitting in would feel cool, nice and cool, because heat is being pulled into the chemicals. As we hold this flask, it's going to feel cold because it's taking heat from the flask. So this would be endothermic. The memory clue is nice and cool. Number 16. Explain what stresses would cause equilibrium to shift to the left. Okay, we want this to go that way. So to make things go to the left, first off, if you remove any of these guys, it'll go to the left. So we need to remove reactants. These are the reactants. Or if we were to add ammonia or heat, let's call this heat, or we could add products, that would make this reaction go that way. Now we got to take a look at pressure. We've got 4 moles of gas, 4 moles of gas, 1 mole of nitrogen, 3 moles of hydrogen. We have only 2 moles of gas over here. This would, I'm drawing the moles of gas as bubbles. This is half the size. So what'll happen is, if we want this reaction, now if we were to squeeze this, increase the pressure, it would drive equilibrium to the right. We don't want that. We want it to go the other way, so we would need to not squeeze it or lower the pressure. So lower pressure will also change the reaction to the left, which is what we want on this one. So removing reactants, adding the products here, whether it's ammonia or heat, or if we lower the pressure. Number 17, what stresses would cause the equilibrium to shift to the left? Oh, okay, sorry everybody, this was a, we kind of did a goof there. I was supposed to fix this one. I think I told my other classes to change that to right. Well, okay, forgive me, I'm gonna make this one right. Sorry about that. So just the opposite's going to happen now. We got the same equation. I'm just going to mark this as heat. This time we want the reaction to go to the right. Sorry, classes, that I didn't catch that sooner, but oh well, you'll live. So we want the reaction to go this way. Well, if we want the reaction to go this way, we need to remove what's on this side. So I'm going to label this as reactants and products. So we're going to remove products. So we take this away. If we take away something, if we use the teeter-totter, if we take away something here, now look at the scale, this little balance dips down. That's not shifting to the right. What's shifting to the right is that, oh, I'm sorry, I did that wrong. If we remove stuff from this, the scale is going to tip up like this, okay? And to get it balanced, now we need to move things to the right in order to get it balanced. So if we remove products, or if we add reactants, if we add over here, if we add stuff here, the scale tips like this, and we have to still shift things to the right. Add products. Now, this is the same equation as that one. We've got this big 4 moles of gas and only 2 moles of gas on this side. So now, if we squeeze this, it'll push it to the right, which we want. So we want to increase. So raise the pressure. Increase the pressure. That'll favor equilibrium going to the right. Number 18, explain what stresses would not, oh, I hate these not problems, would not cause equilibrium constant to shift. So we don't want it to shift. Well, okay, that, Well, if we don't want it to shift, if we want equilibrium to stay the same, okay, then we don't add any reactants, we don't add any products, we don't take anything away, we don't change the heat. On this one, we would not change the pressure. Okay, so you may get a question on the test that'll be like this, but there'll be A, B, C, and D, and they'll give you a little example. So, you know, if they said increase reactants, well, if we increase the reactants, this is reactants, these are products, it's going to cause equilibrium. If we add stuff here, it's going to shift that way, and we don't want, according to this problem, be careful of the knots, so that could not be. You just have to work them one by one. I'm not going to go into more on that because you just work each one. Number 19, in a reversible reaction seen above, chemical equilibrium is obtained when the concentrations, okay, so when this one here, a couple of things can happen. When the concentrations remain the same. See, when we mix this stuff together, there's going to be a reaction, but then pretty soon it's going to look to us like, okay, the reaction's done. We're not going to see a little bit of this stuff forming here at the exact same rate that it forms here. But we're going to get a stable concentration. Maybe we're going to have 0.2 moles of ammonia, and over here we have 0.1 moles of each of those. I'm going to draw square brackets that represents concentrations in moles per liter. Once we get to equilibrium, this concentration stays, for example, let's say at 0.2 moles, and each of those stay at 0.1 moles until you tweak it or shift it. So once the concentrations equal out, they stop increasing or decreasing, they stay the same, they always stay at 0.2 or they always stay at 0.1 here, you've got equilibrium. Or you can say once the reaction rates are the same, because once the reaction rates, once this arrow's speed equals this one, then you're at equilibrium. Number 20, increase in temperature will favor this type of equilibrium. So increase in temperature, I recommend let's do reactants and products. Okay, if you get a question like this and they don't give you an actual equation, you can set up something like this. An increase in temperature will favor this type of system at equilibrium. Well, let's see. Endothermic means we're adding heat, so we need to have plus heat. This is endothermic. Exothermic would just be the opposite. We'd have reactants reacting, and they'd be making a product plus heat. So an increase in temperature will favor this type of equilibrium at rest. Well, what's going to happen is if we add heat to this problem, equilibrium is going to shift to the right. If we have this setup, we have exothermic, if we add heat, it's going to shift it to the left. So if we add increase in temperature, it's going to tend to favor adding heat is going to tend to favor going to the endothermic as we got it set up, because we add heat, it's going to shift it in this direction. If we add heat here, it's going to go away from the endothermic reaction, and so, because if we add heat, it's just the reverse of this now, and you've turned it into this. So the endothermic reaction favors, when you add heat, it'll favor the endothermic reaction. Number 21, a decrease in temperature will favor this type of equilibrium. Well, okay, so we're kind of looking at these. If we remove heat from this one, let me get rid of these arrows now. If we take away heat on this one, okay, heat plus reactants, change back over here. If we remove heat, take heat away, it's going to make equilibrium shift this way. If we've got this equilibrium set up, exothermic, if we remove heat, okay, we take heat away, it's going to shift this way. What's happening is equilibrium is shifting in both these, if we remove heat, to favor this reaction here. They're both going towards making heat, and exothermic reactions make heat, so it'll favor the exothermic reaction. Over here, if you're forming heat, if the reaction goes this way, that's an exothermic reaction. Which way will equilibrium constant shift if there's more reactants added to the system at equilibrium? So, okay, we've got reactants in equilibrium with the products. Which way will it shift if there's more reactants added? Okay, if we add more of this, I'm just going to add more of this. Well, okay, whatever you add, equilibrium shifts the other way. It's going to shift it this way. If you want the little balance here, if you have this at equilibrium, then you add more reactants. This gets heavy. Now, you have to shift things to the right in order for it to get back to equilibrium. Which way will equilibrium constant shift if there's less reactants added to a system? Okay, I'm thinking here they're saying you remove reactants. They were trying to keep the wording reactants. I misspelled that, sorry. So if you remove reactants, okay, draw a little diagram. Reactants, products. If we remove this, if we take away something, equilibrium shifts towards what you remove. If you want to do the little balance thing, if we take away teeter-totterers on this side, the teeter-totter is going to flop up like this, so equilibrium has to shift this way. Things need to start moving that way to become balanced. And lastly, number 24. What must be done to a system at equilibrium to increase the rate of collisions between reactants? Well, let's see here. Reactants, draw the diagram, products. What must be done to a system at equilibrium to increase the rate of collisions between reactants? Well, you can either add more reactants, because if you get more reactants in there, they're going to be colliding with each other more. Or if there's a way you can just increase the temperature of the reactants, if that would be possible, that would also cause more collisions and shift the reaction to the right. So what must be done to a system to increase the rate of collisions between reactants? Increase the temperature or add more of them. Okay, so there we go. Done.